Hello, calculus students and seekers of truth. We are going to kick it up a couple notches here as we find the second derivative when we are working with parametric curves. Right? In other words, how fast is the first derivative changing? Okay? And the key thing here is that we want to do all of this. It's kind of weird. We want to find the second derivative, and that's what this notation really means. I know it looks really weird and unusual, and I'm not sure what was the motivation for writing it this way, but this is just another way of saying like y double prime of x. Okay, that's just all it really means. Now, but the key thing here is that we want everything in terms of t. Okay, in terms of t instead of x and y. Okay. So we want to find the second derivative, and the meaning here is whether the graph is concave up or concave down, but at some moment in time, which is what usually the parameter means. Okay. So let's start out with what we already know. Okay. So one thing that we know to be true is that g prime of t over f prime of t is equal to big F prime of x. Okay, where y is equal, I should write this out better, where y is equal to big F of x after eliminating the parameter. Okay. So another way that we've written this before is that dy dt over dx dt is equal to dy dx. Okay. Now we are going to take the derivative with respect to t. So again, take the derivative with respect, and I'm going to abbreviate here, with respect to t, to the variable t. Okay. So I'm going to do some notation here that may be a little bit weird, but it'll really help us just simplify the process a little bit. So d dt, so the derivative with respect to t of this entire left side is equal to, now we want to know the derivative of f prime of x, so this is f double prime of x. Now, however, x again is a function. X here is a function of t, so we have to multiply it by the derivative of x. So in other words, x prime, or we can just write little f prime of t. And now let's do a little bit of rearranging. We get, let's see, d dt of g prime of t over f prime of t, all of this over f prime of t is equal to the second derivative with respect to x. And again, there's another way to write this that's a little bit more common to textbooks and such. So this is going to be d dt. Now this part in here, g prime over f prime, well, we already know that's equal to the derivative with respect to x, which is also equal to dy dx. And again, this is just notation. I'm just writing the exact same thing, but in a slightly different way. Okay, so the derivative with respect to t of dy dx over f prime of t, which is the derivative of x with respect to t, so I can also write it this way, dx dt is equal to, this is the second derivative with respect to x. Okay. Now, the original big F is equal to y. So this is like saying the second derivative of y with respect to x, which is exactly what we were looking for. So this is d squared y over dx squared, and this is just another notation, another different way of writing the exact same truth. Okay, but this one here, oddly enough, is more common in a lot of textbooks. Okay. So I think I should, show you how this example comes into play with how this idea comes into play with the example that we've seen from before. Okay, so given x equals this, y equals t cubed, find the second derivative when t is equal to 5. Now, we've seen this example before where we could just eliminate the parameter, but I want to show you that it is much more elegant if we actually use this complicated mess over here. So first, before we find the second derivative, we have to find the first derivative. Find dy dx. Okay, and I've done in this previous video, so I'm just going to go through this kind of fast, which is equal to dy dt over dx dt. Now, the derivative of y with respect to t is 3t squared, and the derivative of x with respect to t is 2. So there we go. That's dy dx. Now, the second derivative is equal to the derivative with respect to t of the first derivative. So this is dt of 3t squared over 2. Okay. So I'm taking the dy dx and I'm plugging it into here, and I'm going to divide that by dx dt, which is the derivative of x with respect to t, which again is 2. Okay, the derivative of x with respect to t, which is equal to 2. And now, when we take the derivative of the top with respect to t, we get 6t over 2, which is just 3t, all divided by 2 here. So this 3t is the derivative of this part right here with respect to t. Okay. So now we want to find the second derivative when t is equal to 5. And this should be pretty nice and straightforward. You take the general formula here and you plug in 5. All of this over 2. So we get 15 over 2, or 7.5. Okay. And again, I want to stress and hammer home this point, what this really means, because you might ask, well, this is crazy. You wanted me to find dy dx, and you want me to find d squared, the second derivative of y over x, but you're giving me this expression in terms of t, and that doesn't make any sense. Well, when you think about this in this case, all t here really does is help us find x and y. All along, t is a parameter that helps us to find x and y. So this is like saying if t is equal to 5, how fast is the derivative changing? Okay, so I'm going to have to make my window a little bit bigger here so we could see all of it. Okay, so that looks a little bit better. So trace, when t is equal to 5, we're at that point, right? And this is basically saying that the slope at that point is changing at a rate of 7.5. Okay, so the slope is not 7.5, but the slope is changing at a rate of 7.5 when t is equal to 5. Okay. Now, if these expressions were different, then when t is equal to 5, the results might be different. So it's like x depends on t, y depends on t, and we can still solve for dy dx, and we can still solve for the second derivative, d squared y over dx squared, given a particular t value. There's a way to do this without this method. We could just eliminate the parameter and repeat the process over and over, but that's a much more complicated way than the way we're approaching it here. Alright, so that concludes what we have so far on parametric curves and calculus. We will pick up this concept a little bit later and continue on to build on it. Until then, keep working hard and have a wonderful day.